Welcome back to the lecture on computer-aided design and manufacturing. So, whatever we studied till now, we studied curves, then we studied of the data points which are generated, and from that data points we are trying to form these curves. So, these things which cannot be mathematically represented are called as synthetic curves. So, curves can be divided into two, one is analytical and another one is synthetic. Analytical means where there is a clear definition of equation available. So, where there is no clear definition of equation available, then we go for synthetic curves. Easy to enter the data and easy to control the continuity of curves to be designed, we use this synthetic curves. Requires much less computer storage for the data representing the curve. Having no computational problem and faster in computing time, we have this Hermite cubic spline, Bézier curve, B-spline and rational B-spline curves coming into existence. Hermite cubic spline. In Hermite cubic spline are more general form of curve that can be defined through a set of vertices points. This can be represented by a set of vertices points. A spline is a piecewise parametric representation. Spline is a representation of the geometry of a curve with a specified level of parametric continuity. So, moment I said cubic, it is the third order. Each segment of the Hermite cubic spline is approximated by a parametric cubic polynomial to maintain a C2 continuity. I will leave it to you guys to read, or I will share you a reading material about C0, C1 and C2 continuity. So, then you can appreciate what is C2 continuity. So, the parametric equation of a Hermite cubic spline is given by Pu is a summation of this. So, Ci ui, where u takes the value from 0 to 1. In an expanded form, the same equation can be represented like this, and u is a parameter, Ci is a polynomial coefficient. These are all polynomial coefficient. So, if you wanted to work in a simple form or a algebraic form or a longhand form, so then we will take it by this. But in computers, what we do is we always try to convert this into a matrices form, and generally Hermite cubic spline is expressed in this form in matrices, where 1 u square u cube, these are the u which is taken, this is the coefficient, that is Cij, and these are the points. So, in Bézier what happens is, you can see that the same, if you want to express in the same matrices, you can see here Bézier matrix, these are the points and you have these u which are there. So, Bézier curve properties, the Bézier curve passes through the first and the last control point while it maintains proximity to the intermediate control points. As such, the entire Bézier curve lies in the interior of a convex hull of a control point. This is what we study in mathematics, concave and convex hull. If a control point is moved, the entire curve moves. Being polynomial function, Bézier curve are easily computed and infinitely differentiable. You can split. If the control points of the Bézier curve are transformed, the curve moves to the corresponding new coordinate frame without changing its shape. So, this gives you a freedom of transferring it from one software to the other software without any difficulty. Or you have a user coordinate system, you have a world coordinate system. From the world you go to user coordinate system, from user you go to another user coordinate system. The object whatever you have created will be shifted without any deformation or change. B-spline can be of any degree, but in computer graphics the degree of 2 or 3 are generally found to be sufficient. You can go to nth degree, you will have more data. When you have more data, you will also have more errors coming here and there. So, it is better to stop with 2 and 3, and you also make it computationally little easy. The third order polynomial equation requires 4 set of data points when you talk about 3D. The polynomial between xi and xi plus 1 can be defined as function of x ai plus ai minus 1x, ai minus 2x and ai minus 3. Substituting the value of xi and xi plus 1 in the above equation, we get to solve for getting the constants. The B-spline curve have the flexibility of choosing the degree of curve irrespective of number of control points. With 4 control points, it is possible to get a cubic Bézier curve with which B-spline curve one can get a linear, quadratic or a cubic curve. A B-spline can also be used the bias function or the blending function in the equation to get to this form. The B-spline properties. The plotting of B-spline curve is done by varying the parameters of u over a range of naught values. The naught vector adds flexibility to the curve and provides better control of its shape. The partitioning of unity for any knot span ui and ui plus 1, you get this. The positivity is this value. This is how it is represented. The curve follows the shape of a control point and lies in the convex hull of the control point. The entire B-spline curve can be affinitely transformed by transforming the control points and redrawing the curve from the transformed points. B-spline exhibits lot of local control which is not there in Bézier. The B-spline properties for CAD. The local control can be achieved by changing the position of the control points. You are now getting into fragmenting the curve and moving each individual fragment. The B-spline curve tightens by increasing its degree. As the degree of the B-spline is lowered, it becomes close to the control polygon. If k is equal to n plus 1, then the resulting B-spline curve is a Bézier curve. If k is n plus 1, then the resulting Bézier is a B-spline. If the B-spline curve is contained within a convex hull of its control points, then this is very important. Affine transformation of the coordinate system do not change the shape of a B-spline curve. Increasing the degree of the curve makes it difficult to control, hence cubic B-spline is sufficient enough to do majority of the applications. So, now what is happening, we found out that B-spline also has some difficulty. In order to get out of the difficulty, we went to rational curves. A rational curve utilizes the algebraic ratio of two polynomials. They are important in CAD because of their invariance when the geometric transformations are applied. This point is very, very important. This brings a difference between or the advantage of B-spline on this rational curves. Rational curves gets this advantage. The rational curves defined by n plus 1 point is given by Pu in this form, where u takes a value between u max, where ij is a rational B-spline basic function and it is given by this function. The uniform cubic B-spline are the curves with the parametric intervals defined at equal length. The most common scheme used in all CAD systems is the non-uniform rational B-spline, allowing a non-uniform knot vector. It includes both Bézier and B-spline in NURBS. So, the rational form of B-spline can be written in this form, and where W are the weightages. So, it gives you more freedom for locally changing the curves. NURBS, they have all B-spline surface abilities. In addition, they overcome the limitation of B-spline surfaces by associating each control point with a weight. Uniform representation of large variety of curves and surfaces can be done by using NURBS. NURBS are invariant during geometric transformation as well as projections. NURBS is flexible for designing a large variety of shape by manipulating the control points and the weights. The weights in the NURB data structure determines the amount of surface deflection towards and away from the control points. It makes it possible to create curves that are true conic sections. Surface based on conics, arcs and spheres can be precisely represented by NURBS. So, more and more flexibility is given for the curves such that you can try to make it free form curves. So, the evaluation of NURBS is reasonably faster and numerically stable. Number facilities available in NURBS such as knot intersection, refinement, removal, degree of evaluation, splitting makes it more and more flexible through the design process. NURBS surfaces can be incorporated in the existing SolidWorks by stitching the NURBS surface to a solid. So, if you want to add a patch, to the solid surface, it is possible. Reverse engineering is heavily dependent on NURBS. So, wherein which you have a point cloud data. So, the problem with the NURBS is analytical curves and surface requires additional storage. NURBS parameterization can often be affected by improper application of weightages, which can lead to subsequent problems in the surface construction. Not all geometric interrogation techniques works very well with the NURBS. So, NURBS also has its own difficulty. When we talk about solids, so all these things we are talking about 2D synthetic curves. When we talk about solid models, there are 6 different varieties of solid model. The most common one, which is boundary representation, this is a solid. The solid is divided into several boundaries. So, each boundary is stored. The object is represented by means of a bounded face that is enclosed here. So, this solid is bound each boundary. And when you want to do some fluid analysis now, boundary representation is very important. Each face is represented by its bounding edges and vertices. So, an object is split into several boundaries. Next is constructive solid geometry, which we discussed. So, constructive solid geometry is the representation by the order tree following a Boolean operation. You try to get the solid model. Non-terminal nodes represent Boolean operations such as regularized union, intersection or difference. The terminal nodes represent a primitive solid and the transformation data. So, this is how it is. The solid can be drawn through constructive solid geometry. It is not a unique way, there are several ways. The Boolean operation, you can use several ways to represent a solid. The third one is cell decomposition. The object is represented as a sum or union of set of cells into which it is divided. So, it is divided into cells. So, each cell. The disjoint cell can be of any shape and size. This representing technique is based on the finite element modeling. So, cells are used when you used in finite element, the cell decomposition method is also exhaustively used. Spatial occupancy enumerance. The object is represented by a list of cubical disjoint space. This is a disjoint space. This is a special case of cell decomposition, previous one, where the shape of the cell is cuboidal. This is cuboidal. You can also have any other shape. This is cuboidal. So, this way of representing a solid is spatial occupancy. Then it is primitive instancing. The object is represented by a set of solid primitives such as cuboid, curves, cones, etc. Each primitive is usually defined parametrically and located in a space. So, this becomes easier. Representing a cube in a parametric form is easy. I take a primitive with respect to parametric and then I join to get a shape. Sweeping, which we have already seen, sweeping can be used in making a solid model. The object is represented by moving a curve or a surface along some path. The method is useful to model constant cross-section paths and symmetrical paths. So, you can see here how the edges are formed. So, you can see vertices, these are vertices, vertices to edge, edge to line, line to face. This is the last way or representing a solid model. So, all these 6 methods are used to represent a solid. So, constructive solid geometry, which is otherwise called as CSG. The CSG is a model method that defines the complex solid shape as composition of a simple solid primitives. So, here simple solid primitives are already discussed in the previous lectures. So, I have also listed it out here. So, the terminal nodes can be either primitive or a primitive with transformation. Non-terminal nodes are either Boolean operation or a solid object motion. So, each non-terminal nodes represents a combination of 2 solid primitives in trees. The last one is the feature recognition and design. The feature recognition involves the identification and grouping of features feature entities through a geometric model. Such post definition or features can be done interactively or automatically. So, as soon as the CAD is drawn, the feature extraction is done. Usually, identifying entities are extracted from the model and additional engineering information such as tolerance and non-geometric attributes are then associated with the feature entity. So, you can see here a user, a CAD software, you have a geometric model. So, the feature recognition procedure is followed, feature extraction procedure is followed, and then what you get is a feature model. So, the predefined feature is here and the feature template is here. So, what you do is you try to, for example, I told you already I have a face. So, it quickly goes, there is a template, it quickly goes, identifies what are all the features are same, and then it starts doing it. Suppose hair is there, so it all predefined features are already available. So, it splits it, moment it sees the full CAD model, it gets into, it divides into several features, and each feature is a recognition is one and then extraction is two. Recognition, extraction, this goes back and forth. So, recognition is based on the feature eye, nose, mouth, hair. Template, feature templates are extracted procedures are there. So, we do it and then finally what we get is a feature model. The feature based model design by feature or so called feature based design used a 2D or a 3D feature as design primitives on the product model. The use of feature provides a more natural interface between design and solid. In mechanical design, for example, a designer can work directly with a high level entities such as pocket rather than associated low level entities in which the vertices and edges form a pocket. So, in mechanical design you see here the designer can work directly with the high level entity as a pocket, that is what I said in a face eye rather than curves and lines talking about. The feature allows the capability of providing additional information useful for the planning. Since the manufacturing reflects specific manufacturing process, they assure the part can be produced. So, the feature based design. So, you see here a CAD software, geometric model, feature model. So, feature you pick it up from the feature library is there, a process library is there, you try to get and then see what is going on. The integration of design by feature or feature recognition is applicable for design and manufacturing integration. The user can create a context dependent representation that is specific or informative enough to satisfy the required application. While the recognition process, the user builds the geometric model of a part that is successfully mapped in the feature based. Okay. So, on the other hand, intersecting features, these are very important. Intersecting features are present on the conventional representation and not generated by the feature operation. Intersecting features, I have a cup, I have a ear. This is a intersecting feature, the handle getting integrated are represented in the conventional representation and not generated in feature operation. The algorithms needed to extract both intersecting and interacting features by operating on different input representations are available today. So, with this we try to do feature interaction and feature extraction. Interaction and extraction is done and we try to get the 3D object. The feature interaction problem can be treated as a problem of feature relationship. What is the relationship with respect to a eye and a face? So, that is what is relation problem with the relationship. There is no existing feature recognition system that could recognize all 3D solid primitives as of today. The remainder of this section defines the problem of the interacting features with an example. The interacting features are very common on manufacturing design objects. Feature based design. The design by features or a so called feature based design uses a library of 2D and 3D features as design primitives on the product modeling level. The use of these features provides a more natural interface between design and solid model. In mechanical design, for example, if there is a pocket, so this pocket is fully taken into existence rather than splitting it into lines and planes. The feature allows the capability of providing additional information used for process planning. So, when we try to do a CAD solid model and then leave it for the CAM software to decide, it quickly recognizes individual features and then it extracts and links it with the process parameter. Since features reflect simple manufacturing processes, they assure the part can be produced. So, this is how the procedure is. So, you have a CAD software wherein which you do geometric modeling and you have a feature modeler. This comes and does extraction of the feature modeler, which feature modeling, and then this talks to the user is the designer. So, you have this CAD software which has these two, feature modeler does this, and then this feature modeler always tries to get the information from the feature library, which is in turn attached to a process library. Just by knowing the feature, you see now the process is pulled down and you try to get it. So, this is a simple schematic diagram of feature based design. The integration of design by feature and feature recognition, design by feature and feature recognition is applicable for design and manufacturing integration today. So, design feature is the designer one, feature recognition application is the manufacturing one. A user can create a context dependent representation that is specific and informative enough to satisfy the requirement of the application. While in the recognition process, the user builds the geometric model of a part that is successfully mapped into the feature based model. The feature recognition is also used to directly recognize features from the CAD model. It is easy to derive a geometric feature from a higher level entities of a part model in which each feature is associated with a component of a solid model. On the other hand, to transform the geometric model into a feature representation is very difficult. Intersecting features are represented on conventional representations and not generated by feature operation. Intersecting features are always a challenge, For example, you have a cylinder, you have a plane, cuts it and then you get an ellipse, and now if you so call this ellipse is attached to some other cylinder. So, then it is an intersecting feature if it goes like this, a cylinder and other cylinder going. Okay. Intersecting features are represented on conventional representation and not generated by feature operation. There are several algorithms are used today to for extracting both intersecting and interacting features. The feature interaction also takes a different means in the process planning. If the set of machining features is not machined in the correct sequence, no feature can interact with another feature already in the part, thus generating an incorrect part. So, now what are we talking about? CAD to CAM link we are talking about. All these things are rapid manufacturing. Just doing CAD alone does not matter for manufacturing. So, doing CAD and transforming the data to CAM and doing it automatically needs all these feature recognition model. The feature interaction problem can be treated as a problem of feature relationship. There is no existing feature recognition system that could recognize all type of 3D solid feature primitives and their various interacting combinations. The remainder of this section defines the problem of intersecting features with an example. The interacting features are very common on manufacturing design objects. In this lecture, what all we saw was in the entire CAD, we saw what is the function of CAD-CAM, what are the CAD-CAM standards, what are the function of geometric modeling, importance of synthetic curves, Bézier, B-spline, NURBS, then define constructive solid geometry, constraint based model, explain CSG, then feature recognition, then what defined designed by feature and explain its procedure, what is feature interaction. So, these are the topics we saw in this lecture of CAD. This is very important. If CAD does not exist, CAM does not exist. If CAM does not exist, rapid manufacturing does not exist. In CAM comes RP also, CNC machining, CAE, CAQ, whatever you say. All these things come from CAD. So, if you know to represent CAD properly, then the next step is taken care. CAD, you have geometric, simple geometric and complex. You have analytical surface and freeform surface or synthetic surfaces. So, in analytical surfaces, parametric forms can be done. In synthetic surfaces, you have to work on features like curves. So, these curves are B-spline, Bézier, NURBS, all these representations you have to use for developing a freeform surface using synthetic curves. When you, till now we were only talking about a single curve. Suppose you have a big curve and we are discretizing it into several small curves and the radius of each curve is changing, then the problem of first getting continuity and then smoothness of the continuity and control points in each curve is a challenge. Then we have done this, then we have taken it to the next level, feature recognition. Today the talk of the town is feature recognition through CAD is a talk of a town. One is extraction of details, the two is interaction, or when there is a intersection of details, then how do you extract those features? This is what we saw in this lecture. Thank you very much.